Today we'll dive into 4 exciting topics: machine translation, chatbot enhancements, statistical alignment, and the clustering. Now, I know what you're thinking. How can I juggle all these advanced NLP concepts without my brain overheating? Well, don't worry. I've carefully structured this lecture to make sure you not only understand these concepts, but also feel ready to apply them in your projects. We'll start by exploring how machines translate languages. Then we'll talk about improving chatbot capabilities so they can finally remember that you like pineapple on pizza. And yes, we'll delve into statistical alignment and clustering. Let's get started by warming up with the fascinating world of machine translation. Machine translation refers to the automated conversion of text from one language to another. It has evolved through 3 primary phases: rule-based systems, which rely heavily on predefined grammar rules; statistical machine translation, SMT, which uses probabilistic methods and aligned bilingual corpora; and neural machine translation, NMT, which utilizes deep learning models for more accurate and fluent translations. Each phase has tackled the inherent challenges of translation, maintaining linguistic meaning, grammatical correctness, and cultural nuances. For example, translating "it's raining cats and dogs" requires contextual understanding, as a literal translation would make no sense in most languages. Let's move forward to explore SMT in more detail. Statistical machine translation, or SMT, uses probabilistic methods to determine the most likely translation of a given text. It works by aligning phrases between a source and target language using bilingual corpora. For instance, if red apple frequently appears alongside manzana roja in a dataset, SMT assigns a high probability to this alignment. Phrase-based SMT was a significant improvement over earlier word-based approaches because it allowed systems to preserve context and structure within phrases. However, SMT struggled with long-distance dependencies in sentences, making translation sound less natural. This limitation set the stage for neural machine translation, which we'll discuss next. Neural machine translation uses deep learning models to generate translations that are contextually aware and fluent. At the core of NMT sequence-to-sequence models, which use an encoder to process the input text and a decoder to generate the output text. NMT's use of attention mechanisms was a game changer. Attention enables the model to focus on relevant parts of the input sentence during translation. For example, while translating "the house is big" to French, the model learns to focus on house when generating maison and on big when generating grande. The results are significantly better than SMT, especially for complex sentences or languages with different grammatical structures. Let's now explore how these techniques are applied in real-world scenarios. Machine translation is widely used across industries. Tools like Google Translate provide the accessible solutions for everyday use, while platforms like SWI, SDL, Trados cater to professional translators. In e-commerce, MT helps translate product descriptions, enabling global sales. Healthcare uses MT to localize medical documentation, making it accessible to non-native speakers. Despite these advancements, challenges remain. Handling idiomatic expressions and cultural nuances requires advanced contextual understanding. For example, "break the ice" must be translated figuratively to convey the same meaning in another language. Additionally, translating low-resource languages is difficult due to limited training data. With that, let's transition to how these principles apply to chatbot systems. Let's dive into section 2, enhancing chatbot capabilities. Chatbots have become more sophisticated, but still face significant challenges. One is a context retention, the ability to maintain a coherent conversation over multiple turns. For example, if a user asks, "What's the weather like in New York?" followed by, "What about tomorrow?" many chatbots struggle to connect the 2 queries. Another limitation is a personalization. Most bots deliver generic responses, failing to tailor interactions based on user preferences or history. Finally, handling ambiguous queries remains a challenge. A query like book me a table could refer to a restaurant reservation or purchasing furniture. Addressing these issues requires advanced strategies, which we'll explore next. Improving chatbots involves several strategies. First, contextual understanding enables bots to retain conversation history, ensuring responses are relevant to previous interactions. For instance, a travel bot should remember that the user is asking about New York flights when they later ask about hotels. Second, personalization makes bots more user-centric by using preferences and interaction history. For example, an e-commerce bot can suggest products based on previous searches. Lastly, adaptive learning allows bots to learn from interactions and improve over time. These strategies transform chatbots into dynamic, user-friendly systems. Multimodal inputs refer to systems that combine multiple forms of interaction, such as text, voice, and visuals, to create richer and more intuitive user experiences. For instance, instead of a chatbot simply replying in text, it could also display an image, play an audio clip, or even share a video. In education, a multimodal system can provide students with diagrams or videos while explaining a complex concept in real time. For example, a bot teaching geometry might supplement verbal instructions with an interactive 3D model of a triangle. In customer support, chatbots can assist users with troubleshooting by displaying step-by-step images or animations, reducing frustration, and improving issue resolution times. Finally, in healthcare, multimodal inputs can enhance patient interactions. For instance, a bot might analyze a photo of a rash alongside text-based symptom descriptions to provide a preliminary diagnosis. By integrating these input types, multimodal systems bridge gaps in understanding and engagement, making them invaluable across diverse industries. Next, we'll dive into the real-world applications of these systems and how they are transforming industries like healthcare and e-commerce. Now, let's examine a case study to see these strategies in action. This case study examines how chatbots are transforming healthcare by providing accessible, personalized, and efficient interactions for patients. Imagine a healthcare chatbot designed to assist patients in symptom analysis. When a user inputs, "I have a fever and a cough," the chatbot cross-references this information with the patient's medical history stored in the system. For instance, if the user recently reported allergies, the chatbot could prioritize that as a possible cause over other conditions. It might suggest home remedies or recommend visiting a doctor if symptoms persist. In another scenario, consider a patient asking, "Where is the nearest clinic?" The chatbot, integrated with GPS and real-time clinic data, provides location options and even schedules appointments if required. This kind of real-time functionality significantly enhances patient experience and reduces the administrative burden on healthcare providers. Healthcare chatbots also excel in follow-up care. For example, after surgery, a chatbot could check in daily, asking questions like, "How is your pain level today?" or reminding patients to take prescribed medications. This consistent engagement ensures patients feel supported throughout their recovery journey. One of the most impactful applications is in underserved areas. For communities with limited access to doctors, a healthcare chatbot can act as a first line of diagnosis, offering guidance until professional help becomes available. The efficiency and scalability of healthcare chatbots are game changers. By addressing common queries, scheduling appointments, and triaging patients, these systems free up healthcare professionals to focus on complex cases, improving overall productivity and outcomes. Let's now transition to the next section, where we'll explore statistical alignment and how it underpins multilingual applications like translation. Next, we'll discuss Section 3, statistical alignment and clustering. Statistical alignment identifies correspondences between words or phrases in bilingual corpora. enabling machine translation systems to map source language expressions to their equivalents in the target language. For example, red apple aligns with pomme rouge in French. This alignment process is the backbone of SMT and contributes to creating bilingual dictionaries and parallel corpora. By understanding these correspondences, MT systems ensure translations are accurate and contextually appropriate. Let's move on to the techniques behind statistical alignment. Statistical alignment techniques include IBM models, which use probabilistic methods to align words, and the phrase-based alignment, which focuses on translating entire phrases. IBM Model 1 calculates probabilities of word alignments based on frequency in a corpus, while phrase-based approaches improve fluency by grouping words into logical units. For example, translating play the piano as a phrase produces better results than translating each word individually. These techniques are not just limited to translation, but also support multilingual NLP tasks, such as cross-lingual sentiment analysis. Now, let's explore clustering, another powerful unsupervised learning technique. Clustering groups similar data points, making it easier to uncover patterns in large, unstructured data sets. In NLP, clustering is often used for tasks like organizing customer feedback or grouping user queries. For example, in a customer service chatbot, clustering might reveal that users frequently ask about refunds, shipping issues, and product troubleshooting. These clusters help developers create more targeted responses and intents. Let's review some common clustering techniques. 3 popular clustering techniques are K-means partitions data into K-code groups based on similarity. It's simple yet effective for tasks like grouping sentiment in reviews. Hierarchical clustering, it builds a tree of clusters useful for visualizing relationships between groups. DBSCAN identifies clusters of varying densities, making it ideal for noisy data. These techniques are widely used in NLP tasks, from organizing user queries to building recommendation systems. Let's see how clustering supports chatbot training. Clustering plays a crucial role in chatbot training by grouping user queries into meaningful categories. For example, a travel chatbot might analyze thousands of queries and discover clusters like flight booking, hotel recommendations, and visa requirements. This insight allows developers to create specific intents for each cluster, ensuring the chatbot can respond effectively. Additionally, clustering helps identify gaps in the bot's knowledge, guiding future improvements. This process enhances both the bot's accuracy and the overall user experience. Let's wrap up with a summary and resources for further exploration. Today, we explored 4 critical NLP topics: machine translation, enhancing chatbot capabilities, statistical alignment, and clustering. These techniques are interconnected and contribute to building intelligent systems that support multilingual communication, personalized interactions, and efficient data organization. To deepen your understanding, explore tools like TensorFlow for NMT and Scikit Learn for clustering. Datasets like Europarl provide bilingual corpora for translation tasks, and platforms like Kaggle offer projects for chatbot development. These resources will help you apply these concepts in practice. Whether you're fine-tuning a chatbot's performance or exploiting ring machine translation tools, the key is experimentation. These resources will guide you as you build your solutions, deepening your expertise in NLP. Thank you. See you in the next video.